Stat Quest, Stat Quest, Stat Quest, yeah! Hello, and welcome to Stat Quest. Stat Quest is brought to you by the friendly folks in the genetics department at the University of North Carolina at Chapel Hill. Today, we're doing part 2 of our series on general linear models. Last time, we talked about how to do linear regression. This time, we're going to talk about how to use those exact same techniques to do t-tests and ANOVA. We'll do this using something called a design matrix, which is a cool concept that we'll expand upon in future stat quests on general linear models. Let's start with a super quick review of linear regression. Last time, we measured mouse weight and mouse size, and we wanted to learn two things from it. We wanted to learn how useful mouse weight was for predicting mouse size. R² told us this. And we wanted to know if the relationship was due to chance. The p-value told us this. Now let's see if we can apply those concepts to a t-test. In this specific example, we're going to be comparing gene expression between control mice and mutant mice. Mutant mice are just normal mice that have a specific gene that's been knocked out and is no longer functioning correctly. The goal of a t-test is to compare means and see if they are significantly different from each other. If the same method can calculate p-values for a linear regression and a t-test, then we can easily calculate p-values for more complicated situations. Then we can easily calculate p-values for more complicated situations. So now I'm going to walk you through the steps for using the techniques from linear regression to do a t-test. On the left side of the screen, I'll remind you how each step applies to linear regression. On the right side of the screen, I'll show you how those steps apply to t-tests. Step 1. Ignore the x-axis and find the overall mean. To emphasize that we want to focus on the y-axis, I've removed the labels on the x-axis. Here are the overall means for the linear regression and the t-test. The next step is to calculate the sum of squared residuals around the mean. This is SS mean. These are the residuals, the distance from the data points to the lines. In this case, the lines are the overall means. Bam! Calculating the sum of squared residuals around the mean was easy. Step 3. Fit a line to the data. Note, this is when we start caring about the x-axis again. On the left side, we have the least squares fit to the data. However, how do we do a least squares fit to a t-test? Let's start by just fitting a line to the control data. We start by finding a least squares fit to the control data. It turns out that the mean is the least squares fit. The mean intercepts the y-axis at 2.2. This is the equation for a horizontal line that intercepts the y-axis at 2.2. Thus, this is the line that we fit to the control data. Now let's fit a line to that intercepts the y-axis at 2.2. Thus, this is the line that we fit to the control data. Now let's fit a line to the mutant data. The least squares fit is the mean of the mutant data. The mean intercepts the y-axis at 3.6. This is the equation for a horizontal line that intercepts the y-axis at 3.6. Thus, this is the line that we fit to the mutant data. We have fit two lines to the data. Originally, when we did the regression, we fit a single line to the data. However, there is a way to combine these two lines into a single equation. This will make the steps for computing f the exact same for the regression and the t-test, which, in turn, means a computer can do it automatically. This is key because we don't want to do this by hand, ever. This is going to look a little weird, but just bear with me. Keep in mind that the goal is to have a flexible way for a computer to solve this and every other least squares based problem without having to create a whole new method each time. This is the equation which combines both lines for this point. We have 1 times the mean of the control data, 0 times the mean of the mutant data, plus the residual. Yes, this is strange, especially multiplying the mutant mean by 0, but bear with me. If we multiplied things out, the equation for this point would be y equals 2.2 plus the residual. And that sort of makes sense, but just bear with me. This is the equation for the next point. The only difference is the residual. This one is smaller. This is the equation for the next point. The equation for the next. This is the equation multiplying by like on, and a 0 turns the mean off. When we isolate the 1s and 0s, they form a matrix called a design matrix. The design matrix can be combined with an abstract version of the equation to represent a fit to the data. Column 1 turns the control mean on or off. Column 2 turns the mutant mean on or off. In practice, the role of each column is assumed, and the equation is written out like this. Y equals the mean of the control data plus the mean of the mutant data. Now that we have the fit for the control and mutant data down to a single equation plus design matrix, we can move on to calculating f and the p-value. So, step 4, calculate the sum of squares of the residuals around the fitted lines. With the linear regression, that means the sum of these squared residuals is the sum of these squared residuals. Residuals around the mean, and then we calculated the sum of squared residuals around the fitted line. Now we can just plug these things in to our equation for f. F will lead to a p-value. For the linear regression, p-mean refers to the number of parameters in the equation for the mean mouse size. That's one parameter. In the t-test, p-mean refers to the number of parameters in the equation for the mean of the gene expression. That's also just one parameter. For the linear regression, p-fit refers to the number of parameters in the equation for the fitted line. In this case, that's 2. The parameters are the intercept and the slope. For the t-test, p-fit refers to the number of parameters in the line that we fit to the t-test data. In this case, p-fit equals 2 because we had to estimate 2 parameter data. Bam! Let's review what we mice and mutant are. Here's the original data, gene expression for control mice and mutant mice. The first thing we did is we calculated the sum of squares of the residuals around the overall mean. Then we calculated the sum of squares of the residuals around the fit. In order to do this with a single equation, we had to create a design matrix. Once we've calculated the sums of squares, all we have to do is plug the values into the equation for f, and then we'll get our p-value. Now let's do an ANOVA. ANOVA tests if all 5 categories are the same. Here we have control and mutant mice just like before, but we also have control and mutant mice on a funky diet, and we also have heterozygote mice. The first thing we do is calculate the sum of squares around the mean. We do this just like before. We calculate an overall mean value for all of the categories, and then square the residuals and sum them up. No big deal. The equation for the overall mean is just y equals mean expression. That equation only has a single parameter, mean value for all of the categories, and then square the residuals and sum them up. No big deal. The equation for the overall mean is just y equals mean expression. That equation only has a single parameter, the overall mean, so P mean equals 1. Now we calculate the sum of squares around the fitted lines. The equation for the fitted lines has 5 parameters, one for each mean. Therefore, P fit equals 5. Here's what the design matrix looks like. One column per category. Now that we've calculated the sum of squares around the mean and the sum of squares around the fit, along with P mean and P fit, we can plug those values in and calculate F. Triple bam! If we can calculate f, then we've got ourselves a p-value. One last important detail before we're done. The design matrices that I've shown you are not the standard design matrices used for doing t-tests and ANOVA. This is what we used for the t-test in this stat quest. But this is a more common design matrix for the same thing. Both design matrices will get the job done. It's just the one on the right is more commonly used. We'll talk about this one and other more elaborate designs in the next stat quest.
Writing's not that easy, but Grammarly can help. This sentence is grammatical.
Hey, hi everyone, Phil here. Today we're going to do two things. One is to look at the idea of a t-test for testing the significance of individual coefficients. And second thing is we're going to look at the interpretation of a t-test. Because while you might be able to crunch the numbers and come up with a conclusion for the t-test,
Linear Models Part 2, T-Tests and ANOVA. Okay, we start with some data. In this case, we've measured the size of mice that have a normal gene, and the size of mice with a mutated version of that gene. Then we fit two lines to the data. The first line represents the mean size for the mice with the normal copy of the gene. The second line represents the mean size of the mice with the mutated copy of the gene. These two lines come together to form the coefficients in this equation. The mean value for size for the mice with the normal copy of the gene goes here. And the difference between the mean size of the mice with the mutated gene and the mean size of the mice with the normal gene goes here. We then pair this equation with a design matrix to predict the size of a mouse given that it has the normal or mutated version of the gene. This is the design matrix for the observed data. The first column corresponds to values for B1, and it turns on the first coefficient, the mean of the normal mice. The second column corresponds to values for B2 and turns the second coefficient, the mean of the mutant mice minus the mean of the normal mice, off or on, depending on whether it is a 0 or a 1. For example, the first row in the design matrix corresponds to a mouse with a normal copy of the gene. We predict its size by replacing B1 with 1 and replacing B2 with 0. And then we just do the math. And we see that this mouse is associated with the mean of the normal mice. This row in the design matrix corresponds to a mouse with the mutated gene. We plug in 1 for B1 and plug in 1 for B2. And we see that the mean of the mice with the normal gene plus the difference between the two means associates this mouse with the mean for the mice with the mutated gene. When we do a t-test this way, we are basically testing to see if this coefficient, the mean of the mutant mice minus the mean of the normal mice, is equal to 0. But you already know all this t-test stuff. What you really want to know is how it applies to logistic regression. The first thing we do is transform the y-axis from the probability of being obese to the log of the odds of obesity. Now we fit two lines to the data. For the first line, we take the normal gene data and use it to calculate the log of the odds of obesity . Transform the y-axis from the probability of being obese to the log of the odds of obesity.
I can hear you. Can you hear me? Yeah, I can hear you. Oh, okay, yeah, yeah. Okay. Okay, so I just want to change a few things. How can I do that? Do I open the screen? Oh, uh, yeah, yep. Mm. I've got a few things I have to do, but we can do it. What's the next free day? Yeah. Okay, because I just realized here it's got not for commercial use, but it's a free license for non-commercial. Yeah. Okay. That's all right. Just want to make sure I don't get into trouble. Okay, look, what's today? Wednesday, Thursday. What about is Friday or is around 7 all right? Yeah. Yeah. And how do you want me to do it? Through all right, do you have ANZ or something? I can just the bank and yeah, like 1 or 2 an hour, and then while I'm working on yeah. And it's just amazing.
Now we fit two lines to the data. For the first line, we take the normal gene data and use it to calculate the log of the odds of obesity for data and use it to calculate the log of the odds of obesity for mice with the normal gene. Thus, the first line represents the log of the odds of obesity for the mice with the normal gene. Let's call this the log of the odds for gene normal. We then calculate the log of the odds of obesity for the mice with the mutated gene. Thus, the second line represents the log of the odds of obesity for a mouse with the mutant gene. Let's call this the log of the odds gene mutated. These two lines come together to form the coefficients in this equation. The log of the odds gene normal goes here, and the difference between the log of the odds gene mutated and the log of the odds gene normal goes here. And since subtracting one log from another can be converted into division, this term is a log of the odds ratio. It tells us, on a log scale, how much having the mutated gene increases or decreases the odds of a mouse being obese. Okay, now that we know what the equation is all about, let's substitute in the numbers. The log of the odds for gene normal is just the log of 2 divided by 9. And the log of the odds for gene mutated is just the log of 7 divided by 3. Now we just do the math. And that gives us these coefficients. And those are what you get when you do logistic regression. The intercept is the log of the odds for gene normal, and the gene mutant term is the log of the odds ratio that tells you, on a log scale, how much having the mutated gene increases or decreases the odds of being obese. And here are the standard errors for those estimated coefficients. And here are the z-values, aka the Wald's test values, that tell you how many standard deviations the estimated coefficients are away from 0 on a standard normal curve. The z-value for the intercept, negative 1.9, tells us that the estimated value for the intercept, negative 1.5, is less than 2 standard deviations from 0, and thus not significant is less than 2 standard deviations from 0. And thus not significantly different from 2 standard deviations from 0. And thus not significantly different from 0. And this is confirmed by a p-value greater than 0.05. The z-value for gene mutant, the log odds ratio that describes how having the mutated gene increases the odds of being obese, is greater than 2, suggesting it is statistically significant. And this is confirmed by a p-value less than 0.05. Double bam! Now we have seen how some of the linear model concepts for regression apply to logistic regression. And we have seen how some of the linear model concepts for t-tests apply to logistic regression. In short, in terms of the coefficients, logistic regression is the exact same as good old linear models, except the coefficients are in terms of the log odds. This means that all those fancy things we can do with linear models, like multiple regression and ANOVA, can be done using logistic regression. All we have to remember is that the scale for the coefficients is log odds. Triple bam! Regression and ANOVA can be done using logistic regression. All we have to remember is that the scale for the coefficients is log odds. Triple bam! Hooray! We've made it to the end of another exciting stat quest. If you like this stat quest and want to see more of them, please subscribe. And if you want to support StatQuest follows up on Logistic Regression Clearly Explained, which provides the big picture of what logistic regression is and how it works. In this video, I want to dive deeper into how logistic regression works. We'll talk about the coefficients in the context of using a continuous variable, if you can fit a line, you can fit a squiggle. If you can make me laugh, you can make me giggle. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about logistic regression. This is a technique that can be used for traditional statistics as well as machine learning. So let's get right to it. Before we dive into logistic regression, let's take a step back and review linear regression. In another StatQuest, calculate a p-value to determine if the r-squared value is statistically significant given weight. If a new mouse picked from the weight category of regression. We squared your machine. Don't freak out. We also talked about how we can use discrete measurements like genotype to predict size. If you're not familiar with the term genotype, lastly, we could compare models. And we can compare those predictions to the size. Accurately predict. Now that we remember all the cool things we can do with linear regression, let's talk about logistic regression. Predicts whether something is fitting a line to the data. Logistic regression fits an S-shaped logistic function. The curve goes from 0 to 1. If we weighed an intermediate mouse, then there is only a 50% chance that the mouse is obese. Is a classification. For example, classify linear regression, we can make simple weight and genotype predicted by astrological sign and discrete data. Instead, significance that the variable is, we use Wald's test to, in this case, that's it out probabilities and classify new learning map of the data. In other words, we find the line that minimizes the sum of the squares of these residuals, least square. With line, logistic regression doesn't have the same concept of a residual, so it can't use least squares and it can't maximum likelihood. You pick up, so see that for details, but in a nutshell, you pick a probability, scaled by weight, of observing an obese mouse, just like this curve, this much. And of the data, give the likelihood. Example, what variables are is another exciting.
So the author's position is that the government intervention and taxation in the free market should be minimized.
Oh, I get all that.
Linear Models Part 2, t-tests and a no weight to predict works. Specifically, we'll talk about the coefficients that are the result of any logistic regression. We'll talk about how they are determined. Before we dive into the details, let's do a quick review of some of logistic regression's main ideas. To 1. The probability is obability. I want to mention that logistic regression is a specific type which we use to predict obesity, linear regression, a type of linear model. So let's do a super quick weight have size 0. Over on the left, so we can see what we're doing, let's move the logistic to a log 1 axis. 1 into the if we plug p equals 0 is stretched out from 0 to positive infinity on the new y-axis. Axis transforms if you is not statistically significant z-value like the mutated copy of the gene. These two lines come together to form the
Hi there. In this video, we're going to look at how we go about testing multiple hypotheses. So remember, plus, and based on the, in fact, constructing a test of this. So what we should expect is that if we have a regression where some of our coefficients have very high t-stats, then it's unlikely that they're going to be tested. Yeah, so I haven't included any of the x variables which we prove independent variable. Residuals from the restricted regression minus the sum of square residuals for the unrestricted model. Right, so that's the sort of because I know is the way in which we form. Well, table P from our numerator.
This looks, if you have, the same thing is going to be true. You have a population 1 and into level of confidence. So if things like it's called an F distribution, the shaded region of this guy. So once you get through the next few lessons, and so experience a population number 2. So then you have
a 0 course. We are basically testing to see if this coefficient, the mean of the mutant mice minus the mean of the normal mice, is equal to 0. But you already know all this t-test stuff. For the concept by a p-value less.
Hey, big news! You're about to discover how I sold 131,404
Maximum likelihood in your neighborhood. I think that you should learn about it. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to follow up on our series of videos on logistic regression. This time we're going to talk about fitting a line using maximum likelihood. That is to say, we're going to talk about how this squiggle is optimized to fit the data the best. In coefficients, we saw that logistic regression is very similar to regular and fancier models like multiple regression and ANOVA. T-tests and fancy we saw that logistic regression is very similar to regular old linear models. Like linear regression, t-tests and fancy stuff like multiple regression and ANOVA. The big difference is that logistic regression uses the log odds on the y-axis. However, you may recall that in that stat quest I said, just take my word for it that this is the best fitting line. Well, the time for blindly trusting me is over. Let's see how this line is fit to the data. However, before we talk about how lines are fit in logistic regression, let's do a super quick review of how lines are fit in linear regression. We start with some data, and we fit a line to it using least squares. In other words, we measure the residuals, the distances between the data and the line, then square them so that negative values do not cancel out positive values, and then add them all up. Then we rotate the line a little bit and do the same thing. Measure the residuals, square them, and add them up. And the line with the smallest sum of squared residuals, the least squares, is the line chosen to fit best. Okay, now that we remember how to fit a line in linear regression, let's talk about logistic regression. In this example, we are using logistic regression to determine the effect of weight on obesity. These mice are obese, and these mice are not obese. Our goal is to draw the best fitting squiggle for this data. As we know, in logistic regression, we transform the y-axis from the probability of obesity to the log odds of obesity. We can draw a candidate best fitting line that pushes the raw data to positive and negative infinity. And this means that the residuals, the distance from the data points to the line, are also equal to positive and negative infinity. And this means we can't use least squares to find the best fitting line. Instead, we use maximum likelihood. The first thing we do is project the original data points onto the candidate line. This gives each sample a candidate log odds value. In other words, the log odds of this point is 2.1. And then we transform the candidate log odds to candidate probabilities using this fancy looking formula, which is just a reordering of the transformation from probability to log odds. Reordering using this fancy looking formula, which is just a reordering of the transformation from probability to log odds. For those at home keeping score, here's how to convert the equation that takes probability as input and outputs log odds into an equation that takes log odds as input and outputs probability. First, we exponentiate both sides, and then we divide. Bam! For example, for this point, we substitute negative 2.1 for the log odds, and that gives us p on the squiggle. Now we use the observed status, obese or not obese, to calculate their likelihood given the shape of the squiggly line. We'll start by calculating the likelihood that this mouse is obese given the shape of the squiggle is the value on the y-axis where the point intersects the squiggle, 0.49. In other words, the same as is not calculated as the area under a curve, but instead is the y-axis value, and that's why it's the same as the likelihood. The likelihood on all of the obese mice. Now we'll figure out the likelihoods for the probability of the probability one to the equation. Although it is possible to calculate the likelihood as the product of the individual likelihood is with the log of the likelihood of the thus the log likelihood of the data actual likelihoods. Thus, the points of the original line is negative 3.77. Now we rotate the line and calculate its log likelihood by projecting the data onto it. Calculating the log is in the first line, projecting the data 5. So this one is not as good as the first line, projecting the data to probability. Note, the algorithm that finds the line with the maximum likelihood is pretty smart. Each time it rotates the line, it does so in a way that increases the log likelihood. Thus, the algorithm can find we get a line that bam! There's more to it to have the best fit. But just like with linear regression, there's more to if that line represents a useful model, and that means we need an R-squared value and a p-value. However, in logistic regression, we have to do that without the usual residuals. So we'll learn about R-squared and p-values for logistic regression in the next stat quiz, another exciting stat quiz. R-squared, p-values, effect size, significance. Let's talk about it. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. In this video, we're going to continue our series on logistic regression, and we're going to talk about R-squared and p-values. In the StatQuest, logistic regression details part 2, fitting a line with maximum likelihood. We had weight measurements for obese mice and weight measurements for some mice that were not obese. And we converted the y-axis from probability to the log odds of obesity, and then fit a line to that data using maximum likelihood. Well, technically, we maximize the log likelihood, but either way you do it, you get the same best fitting line. However, we ended with a bit of a cliffhanger. We know that the line is best fit, but how do we know if it is useful? In other words, how do we calculate R-squared and a p-value for the relationship between weight and obesity? The answer is, it's complicated. Although the idea behind this problem, we had weight measurements for obese mice and weight measurements for some mice that were not obese, odds of obesity. Well, and then fit a line to that data using maximum likelihood. Well, technically, we maximize the log likelihood, but either way you do it, you get the same best fitting line. However, we ended with a bit of a cliffhanger. We know that the line is best fit, but how do we know if it is useful? In other words, how do we calculate R-squared and a p-value for the relationship between weight and obesity? The answer is, it's complicated. Although the idea behind generalized linear models, a common framework for solving all kinds of problems, is nice, the result is a bit of a hot mess. Even though pretty much everyone agrees on how to calculate R squared and the associated p-value for linear models, there is no consensus on how to calculate R squared for logistic regression. There are more than 10 different ways to do it. So, before you settle on a way to calculate R squared for logistic regression, look and see what other people are already doing in your field. That will give you a good starting point. For this stat quest, rather than describe every single R squared for logistic regression, I'm focusing on one that is commonly used and is easily calculated from the output that R gives you. Just so you know, this R squared is called mixed. This method is very similar to how R squared is calculated for regular old linear models. So let's do a super quick review of R squared so that related p, we square the sum of, compare that by R squared compares a measure around them. Also, no, there isn't a relationship between weight and size, the data might look like this. Wasn't a relation, the best fit and as R squared equals 0, and the values fit equals 0. And that means when we plug in the values for SS fit and SS mean, we get SS mean minus 0 in the numerator. R squared equals 1. Duh. Now let's talk about R squared in terms of logistic regression. Like linear regression, we need to find a measure of a good fit to compare to a measure of a bad fit. Unfortunately, the residuals for logistic regression are all infinite, so we can't use them. But we can project the data onto the best fitting line, and then we translate the log odds back to probability of the data, -3 for the lit, to SS mean. We do this by calculating the log odds of obesity without taking weight into account, of obese mice, divided by the total number of mice that are not obese. Then project the data onto this at 0.22. Then project the data onto this line. And then we translate the log odds back to probabilities. That gives us a horizontal line at p equals 0.56. 0.22 translates to the overall probability of being obese, 0.56. In other words, we can arrive at the same solution by calculating the overall probability of obesity. Hooray! They are the same. So we have two different ways to calculate the exact same number. Now calculate the log likelihood of the data given the overall probability of obesity. This gives us -6.18. Log like calculate the exact negative overall probability, and you have L and L intuitive sense fit to squared value. Calculating R squared, looking at the R squared there, and there are heavy weight is not a good predictor of obesity. There are light mice that are obese and light mice that are not obese. And there are heavy mice that are obese and heavy mice that are not obese. It makes a poor predictor of obesity. With this data, likelihood, best fitting, and exact, on the log odds scale. For 5, log likelihood value is -6 overall probability. L overall probability of 6 overall we get R squared. Now let's look at the R squared we'll get when weight is an awesome predictor for this data, has an intercept of 2. LL fit because of zero. Data is you log likelihood regression logs and log negative squared. This now the R squared calculated with log likelihoods behaves like the R squared calculated from sums of squares. 1 for good models. Now we need a p-value. Straightforward. 2 times the difference between LL fit squared value with degrees freedom equal to the difference has 2 parameters since it needs estimates for a y-axis intercept and a slope. LL overall probability has 1 parameter since it only needs, in this case, the degrees of freedom distribution with 1 degree of freedom. LL overall, the p-value equals 1 will be closer to negative, will get smaller. We end up with 4.82 for the chi-squared distribution. Thus, the relationship between weight and obesity is not due to chance, and the R-squared value, 0.39, tells us the effect size of this relationship. Trivial to point out. When you see these formulas for R-squared and the associated p-value out in the wild, they will look more like this. This is because the formulas usually include terms for the saturated model. I'll talk more about the saturated model in another StatQuest. For now, however, just know that when doing logistic regression, the log likelihood of the saturated model equals 0, so we can omit it. And when we omit the term for the saturated model, we get the simple equations I've presented in this StatQuest. However, the log likelihood of the saturated model isn't always 0 when it is used with other generalized linear squared model at the end of another exciting StatQuest.